Welcome to the fourth class on power electronics and distributed generation. So, in the last class we started looking at the distribution systems more closely. We are looking at models of the components on the distribution system. We looked at transformer model, the line model, and we are discussing the fault model. So, we looked at the value of the fault impedances that could be used in the system. So, if you have a overcurrent of at least twice the value for the rated for the given section, then potentially protective devices can start operating. So, you are talking about fault impedances starting from a dead short corresponding to ZF equal to 0 to larger values of ZF, but it has to be a small value of ZF compared to 1 to have the appropriate level of current, so that you could actually initiate protective devices. One thing to consider when you are looking at the fault current models in power systems and distribution system traditional protection application, when you are talking about current levels, voltage levels, you are talking about things in RMS time frame. So, if you look at the instantaneous currents, it might be going in a sinusoidal manner. That is what your ideal voltage is, a sinusoidal voltage. Ideally, your current is a sinusoidal current, and its value is going from a peak to a negative peak going through 0. But if you look at it on a envelope basis or on a RMS basis, say if you have a fault, then on an RMS basis you could think about the current level increasing. So, when people talk about instantaneous protection in power systems basis, you are talking about 2 to 5 cycles time frame, and so you are talking about tens of milliseconds. So, you are talking about 10 milliseconds, 20 milliseconds going up to maybe 100 milliseconds, and it is not the instantaneous time that the students in power electronics are typically looking at, where for a power semiconductor device you are talking about switches that can operate in microsecond or in tens of nanoseconds. So, the instantaneous from the power electronics perspective and the instantaneous from the power systems perspective, one has to keep the appropriate time frame in mind when you are looking at how these systems respond. When you are talking about instantaneous trip of a circuit breaker, you are talking about 1 to 3 cycles rather than microsecond level, and on an instantaneous basis from the power electronics perspective, your actual waveform might be a sinusoid, whereas if you are looking at on a RMS basis, you can think of it as a slowly varying quantity, which can vary on a cycle to cycle basis, and depending on the RMS values, you would decide on whether to open a breaker or keep the breaker closed. So, you have to keep the time frame in mind when you are actually discussing the protection level in these systems. So, another model that we would then look at is what would be the appropriate model for power converters in DG applications. So, the simplest power conversion device that you could have for distributed generation is actually an electric machine, and quite commonly a synchronous machine is used, and given the large number of gensets that are out there, the synchronous machine is an important component to consider for what could be a power conditioning system or a interconnection power conversion device that is being used in DG application. So, if you look at a synchronous machine, you can think of it as a voltage behind the impedance model that would be considered. Again, what the impedance is depends on the time frame of analysis that you would consider, and you would be familiar with terms such as your stator inductance or your D axis and your Q axis impedance of the machine for salient pole machines that you would consider for your steady state analysis. If you are looking at shorter time frames, you have your transient inductances. You can have for much shorter time frames subtransient inductance. So, your transient inductance might be of the time frame of maybe a second or so. Your subtransient inductance could be of the order of a cycle or a couple of cycles. So, depending on the time frame you are looking at, you could look at different impedances for the machine. So, if you are looking at typical parameters for these inductances, you are talking about 1.1 per unit. For XS, you are talking about slightly larger impedance for your direct axis impedance of a synchronous machine, because your pole is facing that particular axis. Your quadrature axis in case of a salient pole machine would have a smaller value of impedance. But you can see that the numbers are quite large if you are looking at it on a steady state basis, whereas if you look at for shorter time frames where you might be looking at for faults, you might be looking at smaller value of impedances in the range of say 0.2 per unit to 0.3 per unit for your transient impedance, and you might be talking about 0.15 to 0.2 per unit for your subtransient impedance. So, essentially whether it is a subtransient or a transient, it depends on how deeply into the synchronous machine poles your flux is penetrating. For a sudden change in operation, maybe your flux is penetrating just at the pole shoe level, and you would have your dynamic quantities die out in a shorter time frame, whereas if you are looking at your damper windings etc., it might take longer for your transients to die down. So, you are talking about transient durations depending on the level of penetration of flux into the machine. On a steady state basis, you are looking at the D and Q axis impedances of the machine. Another aspect that is important, especially when you are looking at distributed generation applications where you are looking at not just 3 wire but 4 wire situation, is the zero sequence impedance of a machine. The zero sequence impedance of a synchronous machine can be quite small, of the order of 1% or 0.1 per unit, or it can be even smaller. Essentially, if you look at standard 3-phase windings on because the 3 windings are spatially displaced, if you are applying equal currents in all the 3 phases, which is what your zero sequence component would do, then essentially the fluxes are trying to cancel each other. So, if you get very little flux with the application of current, it means that your impedance is small. Okay. So, you end up with very small impedances. So, you will end up with some unusual situations, for example, in a synchronous machine where your single line to ground faults or single phase faults might end up taking more current than a 3-phase fault. Okay. So, you end up with situations which are slightly unusual when you have situations such as this. If you look at say induction machine, which could be another component which is used as a interconnection device between your distributed generation source and the electric grid. And if you look at your impedance, you are talking about a impedance of about 0.15 to 0.2 per unit. And if you look at the value of the inductance value that is used, it is essentially the leakage inductance of the machine, the sum of the stator and the rotor leakage inductance. If you look at how much current would enter an induction machine when you do a direct online start, common number that people would consider is you would take the 5 times the rated current as your starting current of the machine, and the reason is quite simple. You have 1 per unit of voltage and your leakage inductance is what limits the current. So, that is having a value of 0.2 per unit. You will end up with 5 times 5 per unit of starting current in a induction machine. So, for fault application, when you have a fault on a short term basis, the induction machine would contribute about 5 per unit fault, but again the flux in the machine would decay down. So, it will not last for a long duration of time, but your initial currents could be of this particular order of magnitude. If you look at electronic converter, based power conditioning interconnection, typical power converter that is used to connect with the grid is a current regulated power converter. So, you would be doing current control to ensure the quality of current is a sinusoid. You may want to ensure that the current that you are injecting is in phase in the voltage, so that you get unity power factor. So, often you will have a current regulation. So, you might be able to model your converter's current injection as that of a current source. However, if you look at the converters that are available today, if you have a large transient in the grid, for example, the grid voltage suddenly collapses down, or if there is a big surge in the grid voltage where the value of the voltage goes up, many power converters would just trip and shut down. So, large transients unless you specifically design your converter to actually handle this large transients in the grid, your converter would shut down, but being able to handle the large grid transients is actually emerging requirement, and it is already a requirement for many applications such as wind energy, where if you have low voltage in the grid, you have to have a power converter which is able to ride through the low voltage. So, you have things like low voltage ride through, fault 0 voltage ride through, fault ride through characteristics, etc., which become more and more important for power converters. And again, when you are talking about fault, you are talking about time durations of the order of tens to hundreds of milliseconds. So, your power converter will have to be able to operate for the hundreds of milliseconds when a fault has occurred in the power system and you have extreme imbalances or under voltage levels, and the power converter should operate through that situation without actually shutting down, so that it can come back into operation when once the grid gets back to normal. Okay. So, another the thing that we will consider next, after considering the power conditioning devices, which can be machines or power converters, is what sort of protection equipment would be there on a typical distribution system. So, if you are looking at protection equipment, you are looking at over voltage protection or over current protection. So, if you are looking at over voltage protection, you are looking at things such as surge arresters. So, the type of surge arresters that you would use in your equipment depends on your distribution system. So, for example, whether your transformers are solidly grounded or impedance grounded. So, for example, if you have solidly grounded transformers, it means that your neutral shift when you have a fault would be small. So, you could have lower margins for your surge arresters, whereas if you have impedance grounding, your neutral could potentially shift by a larger amount, which means that your surge arrestor would need to have higher voltage margins. If you are looking at over current protection, you are looking at devices such as fuses, circuit breakers or relays, and if you look at the way the protection is would be done in such devices, you would have you could have thermal, which is essentially thermal overcurrent protection in a fuse. It can be electromagnetic, in a circuit breaker you could have digital trip units. In a relay package, especially newer relay packages come with quite sophisticated digital trip units, and each of these things, for example, a digital trip unit has to be backward compatible with what is already there in the system. So, you cannot make your digital trip unit respond as fast as your processor can calculate, but your digital trip unit should be able to emulate the type of characteristic that is there in a thermal overcurrent protection or the electromechanical relay, so as to have the backward compatibility. So, your newer protection device should be able to operate with your older protective devices. Okay. So, that is an important aspect of power system. You cannot say every fuse has to be replaced by a newer device. So, whatever newer equipment that you are bringing in has to be compatible with your equipment that is already there in the system. Again, as I mentioned, your instantaneous trips have to be is actually on a RMS basis rather than on a real time instantaneous basis that we would consider or on a waveform. So, you are talking about number of cycles to trip even when you are talking about instantaneous. Okay. So, if you look at a fuse, for a fuse you are talking about essentially thermal coordination, and you are selecting your fuse based on its the point at which your fuse would start melting. So, you are depending on the fuse melt curve. Okay. So, if you are looking, if you are thinking about fuse operating at some nominal current levels, the power dissipation in the fuse would be such that it would not heat up to the point where it would melt, but once it goes above some critical value, your fuse will melt depending on the amount of current that is causing dissipation in the fuse. So, you are looking at your melt curve to determine at what point it would melt depending on what current level is actually going through the fuse. The fuses are actually quite reliable, it is low cost. And reliable because there is nothing complicated where you do not do any sensing and evaluation of algorithm. If the current is more, it melts. So, it is quite simple, which lends itself to reliable operation. Okay. But you have other concerns that if you have a 3-phase system, the overcurrent might actually cause the fuse in one phase to melt and not all 3 phases. So, you could have single phasing of lines, you will not be able to ensure that all fuses simultaneously operate. So, you might end up with situations where some loads could potentially face problems when you are actually having fuse as the only protective devices. Okay. Single phasing is a concern, and every time a fuse blows it has to be replaced. So, yes, the replacement is a concern, whereas in a circuit breaker you have a trip, you could reset it and get back to operation. Because it is low cost and quite reliable, often it can be used in it is used in the end of the system where cost is very critical, closer to the end of your distribution radial structure, or it can be used as a backup protection. Say if you are taking a circuit breaker and you want to have backup overcurrent protection for your breaker or your relay, then you could use a fuse to provide backup protection in case your breaker is not operating. Okay. So, your fuse would not typically melt because the breaker would typically operate. In case it fails, you now have a backup protection. If you look at the next device which is commonly used in for overcurrent protection, it is a circuit breaker. And if you look at the circuit breakers that are available, there are bimetallic circuit breakers which operate on a thermal basis. You have electromagnetic circuit breakers, you are many larger size of breakers available today have electronic trip units which actually operate to decide on whether the breaker should open or stay closed. So, you could have different control packages to actually operate the breaker. So, the actual breaker is a device which would make or break the current. Okay. Whether it should open or close is decided by your trip unit. Okay. So, if you look at the ratings of the breaker, you will have both your voltage ratings and your current ratings. So, your voltage rating needs to be based on your based on the voltage level at which you would operate. So, whether it is 230 volts, 415 volts, 690 volts, depending on your application, you would have voltage rating, the voltage at which you are expecting your breakers to operate. The other item that is important is also your isolation voltage. Voltage level, where essentially if you have a voltage spike coming across the circuit breaker or on from one point to your frame, which might be connected to your cabinet, etc. You also have isolation voltage level, where having opened, what voltage it can withstand before things arc over. Okay. So, your isolation voltage is also an important parameter of your breaker. So, often for many low voltage circuits, you would need isolation voltages level of at least twice your rated voltage plus some margin on an RMS basis. So, that even if you are talking about voltage level at which it would operate, your ability to isolate has to be much higher than the ability at which you actually operate. Okay. If you look at your current rating, the current rating of your circuit breaker, there are couple of important current ratings that need to be considered. One is if you select any device, what is the current at which it would typically operate. So, if you are using a circuit breaker which is getting connected to a 10 amp circuit or a 15 amp circuit, you need to have at least the capability of 10 or 15 amps, so that the breaker does not overheat under normal loading conditions. The second aspect of the current rating which is important is, so you use a 10 amps or a 20 amp circuit breaker, but when there is a fault downstream of the circuit breaker, your actual current, fault current is much higher. It could go up to hundreds of amps, thousands of amps. So, how much current can it actually interrupt? Okay. So, the interrupt rating of your circuit breaker is also an important parameter. So, so if you look at the aspect there, so there are multiple issues that you would need to look at before you select a circuit breaker, how it is used and what would be the fault conditions under which it has to protect your actual load. If you think about a circuit breaker, it is a form of a switch. Okay. So, it is a switch that is on or off, but if you look at what are the different varieties of switches that are out there, breakers imply you have the ability to interrupt fault, okay, whereas a normal switch may not have the ability to interrupt a fault. So, if you are using a contactor in a power electronic application, it can carry rated current, it may be able to switch off your nominal current level, but it will not be able to interrupt a fault current level. So, if you try to interrupt fault current level using just a regular contactor, your contactor contacts can potentially melt. Okay. So, you need the structures of your circuit breaker to actually provide the appropriate arc impedance in your circuit breaker and the ability to extinguish the arc and dissipate the energy in the arc. So, you need more extensive structures in a circuit breaker compared to a regular switch. If you are looking at just a isolation switch, you are looking at the ability to maintain isolation voltage. you are not even looking at the ability to interrupt load current. Okay. So, depending on the type of switch that is being used, you would have different levels of complexity. So, because the ability of the circuit breaker is for application which is intended to handle much higher fault conditions, your circuit breaker would be more expensive than just a contactor. So, if something is designed to handle much more challenging situations, you would have associated costs with it. So, depending on what you are intending that particular switch to be applied in, you have to make use of the appropriate variety of switch. If you look at a relay, you can think about the relay as essentially the control package which governs whether the switch needs to open or close, and for overcurrent protection you are looking at a overcurrent relay. So, essentially the relay is a device which initiates whether to trip the breaker, or some breakers have abilities to reclose or close. So, the relays can actually give such commands to a circuit breaker. And tripping or opening. Relays tend to be more expensive. So, it is newer relays are that are available today are mostly electronic relays. So, with a relay now you can actually trip all three phases. So, you can actually ensure that all the phases get disconnected simultaneously. Okay. It can be made more sensitive, and depending on your algorithm it can be made to respond in a fast manner, and it is possible to implement many sophisticated functions like directional impedance evaluations, etc. So, in fact, the newer relays that are available are multifunctional relays. They are often called intelligent electronic devices, IED, and can be used with in a variety of situations. So, if you look at another protective device which could be used in a distribution system, one can think about say a recloser. So, essentially the idea behind a recloser is that many faults are large number of faults are temporary. So, you can if you are able to open the de-energize your line for a short duration and the fault clears, then when you re-energize it you can go back to normal operation without physically someone going there and having some manual intervention. So, if you are able to open your circuit breaker for some time and once the fault is cleared you close it again, you can potentially continue normal operation. But if you have say for example a situation where you have something where there is permanent damage, then when you reclose again you end up with a overcurrent, and so you might try a few times to actually reclose, and at some point you decide that yes, this is actually a permanent fault, then you stay locked out. Okay. So, essentially you would have reclosers are essentially, you can think of it as a circuit breaker with a relay package which can actually reclose a number of times. You can have a programmable number of reclose cycles, say 1 to 4 reclose cycles could be commonly used. And again, for thinking about what the sequence of operation is, it would be good to think in terms of the RMS current levels when you have a fault. So, in this example over here, what is shown is the recloser status, either it is closed when, say here, when the logic is indicated high, and it is open when the logic is indicated low. So, initially it was closed and things were under normal conditions, and say you have a fault at some instant say t naught. So, at this particular instant, say you had a fault which caused your current to actually come up to a large extent, to a higher level, then in a short duration, maybe on an instantaneous basis, depending on you would actually open your recloser. So, after opening the recloser, you wait for some duration, and then where your recloser is in the off condition and the line is de-energized, and then you reclose. And you have two possible scenarios over here. One is the fault has cleared, in which case you go into a current level in this hatched area and you continue operation in the hatched in this hatched zone. A second situation is maybe the fault did not get cleared by this initial pulse of current. So, when you re-energize, you go back to the fault condition. So, your current level continues at the high fault current level itself, and again now you wait for a certain closed duration, and then you again open your recloser. So, you could think about say durations. You might call it as, you can give names for these durations, and so once you have opened again, when there is a fault seen during this first reclose cycle, you again wait for some time and you open the breaker, and so under this open condition there is no current flowing, and here now you try to close for a second time. So, the anticipation is now you have reclosed for a second time, you potentially have cleared the fault. So, you might go back to normal operation, or in case you have something really solid on the feeder, then causing a fault, then you go back to your high current level, you wait for some more duration, and then you lock out. So, at this point, if the fault is still continuing, your recloser will lock out and stop further reclose attempts. So, this is a recloser with 2 reclose cycles. So, you have one opening, a second opening, and then it would lock out if the fault is permanent. And if the fault is temporary, now it has 2 chances to get back to normal after the first reclose cycle or the second reclose cycle. Okay. So, so you can see that if you have a temporary fault on this particular feeder, it would get cleared with minimal disturbance, and you could re-energize and go back to normal operation. So, if you think about the recloser, it can be thought of as a circuit breaker, and the circuit breaker might have its own time over current characteristics, and the circuit breaker might also have a program to actually execute this reclose action. Okay. And if you are having already relays in the substation, you can actually now incorporate this reclose logic along with the feeder circuit breakers sitting at the substation. So, you could look at improving the power quality or the time of uptime of your feeder when there are potentially faults on the feeders. Okay. And this logic can be easily incorporated into your substation protection logic. So, if you look at another item that we had mentioned, we had also mentioned sectionalizers. So, a sectionalizer is a device which is intended to operate along with a recloser. So, suppose you have a feeder coming from a substation. So, you have a feeder and you have branches or laterals on this feeder, and say you locate your sectionalizer on this particular lateral, and you want to actually say isolate this particular lateral when there is a fault on the lateral rather than de-energize the entire feeder. Okay. So, we will see how it can potentially be done. So, suppose you have a fault on this particular lateral downstream of the sectionalizer. What the sectionalizer does is it would count the number of fault current pulses, and it can shut down or lock open after counting a given number of current pulses flowing through it. Okay. So, in this case we will again assume that your upstream recloser has 2 reclose cycles, and you have a fault at this particular location downstream of this on this particular lateral. So, you have multiple situations. If this particular fault was a temporary fault, then this recloser which was initially closed, after its first opening, you potentially, if this fault cleared, you can go back to normal operation. Nothing would change on your recloser or the sectionalizer. Suppose you have this recloser with 2 reclose cycles, and say this sectionalizer is counting for 2 current pulses. Okay. So, in this particular case, you have say a permanent fault occurring at this particular location, and at the initiation of fault at time t naught, you end up with 1 current pulse flowing through the sectionalizer. At the end of your first during your first reclose cycle, you end up with now a second pulse now flowing through this particular sectionalizer, and then through this particular sectionalizer, and then the recloser opens. So, when the recloser opens, essentially the sectionalizer would count now 2 cycles and lock open. So, when the recloser now recloses for a third time, the sectionalizer is open, which means that this feeder can go back to normal operation, and this lateral has actually opened and got disconnected where you have the permanent fault. So, you can see that there are 2 things that are happening over here. The logic for it is not complex, because you are just comparing current pulses rather than doing more complex time over current characteristic. The second thing is the sectionalizer is opening when the recloser is open, which means that you just need a simple contactor type of switch rather than a circuit breaker. So, it is interrupting at low current levels, or ideally at 0 current levels. So, you could have a lower cost device as a sectionalizer. So, in this particular case, you had a 2 cycle recloser and you had a sectionalizer which counted 2 pulses and locked open. So, you isolate this particular lateral and you go back to normal operation. Sectionalizers needn't just be on laterals, it can also be on really long feeders. You may want to sectionalize the tail end of the feeder and the front end of the feeder. So, you could have different configurations. You could also have chain of sectionalizers. You could have sectionalizer 1, sectionalizer 2, depending on how you are connecting your laterals. There are other simple protective devices that are used in the distribution system. You can have fused disconnects, jumpers, etc. Essentially, they are isolation devices which are opened before a lineman comes and works on the particular feeder, or before the person does any repair work on the distribution system. So if you now look at more closely at what is the characteristic that one would need when you are looking at protection in terms of a fuse or a circuit breaker. You are looking at the time overcurrent characteristic of your protective device. And you are looking at fuses, circuit breakers, relays, etc. And so, with a fuse, you are looking at the fuse of the appropriate voltage rating at which it would interrupt the current, and you are also looking at your current rating of the fuse, the nominal current at which the fuse would be expected to operate depending on the downstream loads connected to it, and also the interrupt capacity of the fuse. So, you have fuses of different interrupt capacities. You have some fuses which might need to interrupt high currents like HRC fuses, high rupture capacity fuses, etc. So, depending on the type of requirement, you would need to use the appropriate type of fuse. And aspects of it that are important is what is your minimum melt time. So, the time required for the fuse to melt depends on a couple of things. One is what is the temperature at which it was nominally operating. So, if it was initially operating at an elevated temperature, it can actually melt more quickly. Okay. Another aspect which is important is how much current level is there, because it is the I square R losses in the fuse which dissipates energy into the fuse and causes the fuse to melt. If you think of it as a adiabatic process, which means that energy is going in, it is not dissipating outside, then essentially you would be looking at what is the minimum melt time. Similarly, you would have a characteristic of what is the maximum clearing time. How much would be the maximum time before which the fuse can actually be considered open. Okay. Another aspect of the fuse which is important is suppose you have a fuse and you have some overcurrent flowing through that particular fuse, and the overcurrent is for a short duration, and before it melts the overcurrent went away, then how does the fuse return back to the normal condition. Okay. So, you also have the cooling time constant where the fuse heated up to some extent, then it cools down depending on your thermal time constant of the particular fuse. So, essentially you can think about the cooling time constant as some sort of a reset mechanism of the fuse, where it got exposed to overcurrent, and when the current went away it cools down and resets back to normal operation. If you look at circuit breakers, you are looking at now something people refer to as the IDMT characteristics, or inverse definite mean time characteristic. Essentially it means that larger the current, you will take a short duration for your circuit breaker to operate. If your current level is small, then it would take a longer duration to operate. But even at very high current levels, there is some fixed delay before which your circuit breaker will not operate. Okay. So, if you look at it from your tripping characteristics of your circuit breaker, you can think of a critical level as a pickup current level. If your current is greater than the pickup current level, then you would be initiating tripping action in the breaker. If your current is below your pickup current level, you will be having reset action going on in the breaker. Okay. And you can define a ratio between your actual current and your pickup current, and depending on this ratio m, your circuit breaker would operate with a given speed. So, for tripping, your value of m has to be greater than 1, and your time to trip can be expressed as an expression, say a divided by m to the power of p minus 1 plus b. So, this could emulate the IDMT type of characteristics. Similarly, for when m is less than 1, you would have a reset time, can be again expressed as some TRE divided by m to the power of p minus 1, the absolute value of it. And if you are operating close to your nominal current level, and if your nominal current level is much smaller than your pickup current level, then m can be considered close to 0. So, you could take your reset time to be approximately given by your capital TRE. So, you could consider your reset time to be roughly constant, just to simplify your analysis. Okay. For m close to 0, your TRE is roughly constant. Okay. And in these expressions, your A, P, B, etc. are constants, your TRE, these are constants depending on the type of characteristic you are trying to emulate in your circuit breaker. Okay. So, depending on the value of your A, B, P, etc., you can have different definitions of what would be your inverse current characteristics. So, IEC defines circuit breakers which are moderately inverse, very inverse, extremely inverse, etc. For the time current characteristic. Okay. So, a good reference for this would be IEEE standard C37 -112, which is the inverse time current characteristics for overcurrent relays. So, the type of curves are essentially, if you have a large value for the multiplier, essentially the time required to trip is quite small. So, if your value of the multiplier, which is m, which is the ratio of your actual current by your pickup current, is a smaller number closer to 1, it would take a longer time to trip. So, if you now plot it on a log scale, it would look as curves which are shown over here. Okay. So, for your extreme and very inverse type of characteristics, essentially you could consider P approximately 2, and the expression for your trip time can be written as assuming your B is small, essentially the definite time is small, and for m, which is much larger than 1, you could take this as approximately A by So, if you you know that your m is your ratio of your actual current by your pickup current. So, if you substitute that, So, at this point what we will do is we will wrap up this particular session.